Yeah. So this bucking problem in this case is using Rankine's formula. And what we have here is some sort of column that has a T-shaped section, like this one here. This one here. Yeah. And so it has certain very specific characteristics, such as, maybe it's not commercial, it's something that was done, is custom made. And there are a bunch of things that they are asking there that we might need to figure out later. But they said, okay, let's calculate this column and let's consider that both ends are hinged. And something that I would like to have shown here is how a connection between these type of shapes and maybe a beam or another column would be in case of hinged ends. But I couldn't find a clear picture from the internet to show you guys about that, because it would be interesting to see how in reality that it is achieved. Then I'm providing what's the crushing limit stress for this material, which is 320 megapascals. And it is represented in this way because, let's say, it is part of a Rankine's consideration that columns might fail by crushing or might by a contribution of crushing and a contribution of buckling. And depending on the slenderness of the column, one is going to be more predominant than the other. Rankine's constant is given, and then a safety factor is given. So in the end, what we need to calculate is the buckling load for this application using a safety factor of 3. I have a couple of tables here. The first one notes, for example, what's the ending termination of each one of the columns, because let's remember that the physical length of a column is totally different from the effective length taken into consideration in the buckling formulas such as Euler's, Rankine, or Johnson's formulas. And we need to take care of that because depending on what's the type of ending of the columns, then the possibility of deformation is going to be different in each one of them. Hence, the buckling load is going to be different according to the ending of that column. And as I'm already working ahead, and I know that this section here is a little bit custom, meaning that might be nothing commercially available because there is nothing being said anywhere about this or with manufacturers, but they're only giving me the shape of it, then I might be needing something to calculate, some help to calculate the moment of inertia of this beam, as I know that in my column formulation, I would need the inertia of that column. So I have it here. To start with, let me write down the Rankine's formula, but I'm going to move this aside to put it here, and then this one I'm going to put it here. And Rankine's formula, because I want to start with the formula I need to apply in order to look for those terms that are not readily available to me to perform the calculation. For example, then say Rankine's formula, or let's put it critical load, is calculated using the following, let's say, relationship. It is kind of, we have, let me see if I have the rule, yes. We have the crushing load, we have the area of the section of the column, and that's going to be divided by 1 plus Rankine's constant and the relation between the effective length of the column and the radius of gyration of the column, and this is square. Let's remember that this L presented here is the effective length of the column. Now, the next question is, okay, this is what I have to find. And if I want to go a step further, I can say, well, if I want to find a safe or the safe load, meaning that the load that is found by applying a safety factor as the one mentioned here, then what I would need to do is just divide that critical load determined by Rankines and divided by the safety factor. And the safety factor in this case being 3. Now, let's do an inventory of what we have here. So I have the crushing load, which is given in point number 3 here. I have the Rankine's constant, which is given in point number 4 here. I have the length of the beam, even though the length of the beam, the physical length is 4, and this is what's represented like L lowercase. I can determine what's the value of this effective length because I know that depending on the ending condition, in this case, is both sides are hinged. So this one here, I know that the effective length for this condition is going to be equal to the physical length of the column. And of course, I have this effective length of the column. The area, well, I don't have the area, but I could calculate it because I have all the dimension of these rectangles that form this T-shaped column. And K, we need to know that K is the relation between, let me write it here, is the square root of what? Of the moment of inertia. I don't know which moment of inertia because let's remember that when we are calculating columns, we need to pick the smallest moment of inertia of the column because that's going to be the weakest column moment of inertia where most probably the column would buckle. And that's going to be divided by, if I remember correctly, it's the area, yeah, of this column, of the section, sorry about that. So let me see. Just trying to look for the correct formula for K. Yeah, that's correct. A. Meaning that I need to calculate the area and I need to calculate K. But to calculate K, I need to calculate the inertia of those sections of this, let's say, of this column. And then I know that, okay, I just need to calculate two things, area and inertia. But I know that as this is not a symmetrical section, I would have to calculate two moments of inertia, meaning that I would have to do a couple of, let's say, estimations, not estimations, but application of the formula for inertia on this type of shape to know which one is the smallest one and then use it to calculate the radius of gyration here. Perfect. Now, let's start with the first one. So I'm missing the area. So let's calculate the area of this section. And by the way, if you have a question, please, interrupt me. So we just tackle the question as they are appearing. So let's start with this. Let's use this one. So let's tackle the area. So I know that in this combined section, T section, the area is going to be the sum of the kind of upper part here, the upper rectangle, plus the area of the lower rectangle. So if I want to draw this or kind of signal, so it's going to be the area of this part here, of the upper part, plus the area of this lower part. Meaning that I can divide the whole T section into two rectangles and take advantage of that simplicity. Let's put it so. Then area is equal to the area of the first part, which I'm going to call this A1, and I'm going to call this A2 plus A2. Then area is going to be, A1 is going to be 150 millimeters times 20 millimeters. So I can decide if working with millimeters or meter at the time. And I would say, well, let's keep working in millimeters because I know that megapascals translate straight to Newton per square millimeter. So I can say that, well, I know that 1 megapascals is 1 Newton per square millimeter. And then, well, let's keep working in millimeters here. So, and then it's going to be 150 millimeters times 20 millimeters. So that's the first one, plus area 2, which is going to be, let's take, these are the bases, and then this is going to be 20 millimeters times the height, which is going to be 100 millimeters. So let's make that calculation here. I'm going to use this type of calculator to try to do it online. Let's see. I have 150 millimeters times 20 plus 20 times 100. That's going to give me 5,000. Great. So this is going to be equal to 5,000 square millimeters. So this is the first one. I'm going to mark it in red. So this is one of the pieces of data I needed for to complete, the unknowns I have for this equation here. Great. Now this is done. So this is already known. Now I need to calculate now the inertia. And as I mentioned, this section is going to have two moments of inertia because the section is not symmetrical. So it's going to have two different moments of inertia, most probably. And we need to find out which one is the smallest one too, so we can use it to calculate the radius of gyration. And then after having the radius of gyration, put it back into the Rankine's formula to calculate the critical load for that column. Let's do that. To do it better, I want to draw this section here. So let's imagine that this is the T section. It's going to be some approximates, something like this. Then let's put the length, something like this. Because something interesting is going to happen here when calculating this inertia. Because it's not that we can calculate it right away, with just one formula. It's highly possible that definitely there is existing a formula for T sections to calculate, the inertias for this type of section, which is pretty common, but let's do it by hand because it's going to allow us to, let's say, expand some type of understanding on what's happening here. And it's going to refresh a lot our knowledge about these type of processes. First, I'm going to define two axes. So the first one is going to be the y-axis. I'm going to mark it like this. This is the y-axis. And now, this is pretty simple because according to this vertical line, the section of this section is symmetrical, meaning that I'm for sure I can know if I want to vertically cross this section by their vertical centroidal axis, then this is going to be the position of that line. But now if I try to do the same with the horizontal centroidal axis to this section, I don't know where it is, if it's here, here, or here. So because there is not symmetry when I try to rotate that section around an horizontal axis. So I'm going to put it something like here, just because I know that it's not going to be in any of those places, but I need to calculate where the position of this x-axis corresponding to the horizontal centroidal axis is going to be. What questions do you have? Because this is very important to solve these type of problems. All right. Then I know that to calculate the inertia of these type of segments, I could take advantage also of the fact that these are two rectangular sections tied, at this point, meaning that I could then add both moments of inertia to obtain kind of the definite or the largest, or let's say the total moment of inertia of this section. However, when we define moment of inertia, like this figure that you're seeing right here, moment of inertia is defined with respect to certain axes. And for example, when you find these two first definitions of moment of inertia for axis, for rotation about the x-axis or the y-axis, it says, well, I'm giving you the inertia of this section, but considering this reference system. So meaning is this one here. So from this axis. But if you are, well, I don't want those, I want the moment of inertia, but looking at them, let's put it in that way, from the centroidal axis, vertical and horizontal centroidal axis of the section. When you ask that question, you're going to find out, meaning kind of this one and this one, you're going to find out that the centroidal axis changed the value because they are being looked at from different reference systems. Now the question is here is, okay, from which reference system we look at this uh, moments of inertia. Definitely, I want to look at them from the centroidal axis for the purpose of this problem. I know that the centroidal axis of this y, the y centroidal axis, is located in the middle of the whole section because there is symmetry between these two parts. But when I look at it from the x-axis point of view, I need to find out where that x-axis is located, in the vertical, let's say, dimension. And to find out that, then, we need to find we need to do a procedure there. But first, let me write, we already have here these, and then I know that the moment of inertia is going to be, for my case, by looking at it from the centroidal axis, is going to be equals to 1 divided by 12 times the base times the height to the cube, which is power of 3. Perfect. But now, how much is this distance? So where is this x located with respect to this? So to know that, I need to, let's say, use something called kind of uh, the formula to calculate centroidal axis, which is based on the individual areas of the composite, so or the section that is formed by different, let's say, shapes. And that formula to find that centroidal axis, or the y centroidal axis, mean this line here. So where's the distance between this and this one here? Let me put this one. Try to fix it. Yeah. So I'm going to call this one y. And with the bar here to indicate that I'm going to measure the distance of this x horizontal axis from this point here. Yeah. Right. So then to measure that, I need to kind of assess the contribution of each area to the location of this x-axis. So let's do that. So the formula is something like this. Y bar equals to the contribution of the first area, let's call it that way, it's going to be A1 plus Y1. I'm going to explain that. And then A2, the contribution of the second area. And that's going to be weighted by the sum of the areas. We've done that in the curve pin examples probably, but it's fine to do this again. So I know that area 1 is going to be represented by this piece of equation, this part of the equation, and area 2 is going to be the contribution kind of all determined by this other part of the equation. Y1, who is Y1? It is the distance from this point to the centroidal axis of this first section, meaning this one. This is Y1. And who is Y2? Y2 is going to be the the position of the centroidal axis of the second area measured from this point here. This is Y2. I know that Y1 is half of this distance because the centroidal axis of this first rectangular section is going to be half of it, and that's going to be 10 millimeters. And Y2 is going to be this whole vertical distance, meaning the whole thickness of this uh, upper area, plus half of the distance of this area, because it is also located in the middle of the vertical section of that rectangle here. So it's going to be, this is 20 millimeters plus 50 millimeters. So it's going to be 70 millimeters. Right here. Then I have all the ingredients to calculate this. So let's write it down. The distance from this point to this x-axis is going to be equal to area 1, which is going to be 3,000 millimeters square. Sorry, millimeters. Yeah, millimeters square times y1, which is going to be 10 millimeters, plus the area 2, which is going to be 20, or well, at once I can write 2,000 millimeters, square millimeters, sorry, times y2, which is going to be 70 millimeters. And that's going to be divided by the sum of both area, which happens to be the total area of the section already calculated, and it is 5,000 square millimeters. How much is that going to be? Let's see. Let's bring this one here. So I'm going to have on the upper part 3,000 times 10 plus 2,000 times 70, and that's going to be divided by 5,000. And the answer for that is 34. Let me write it back. It's going to be 34 millimeters. So this distance is 34. Perfect. Now, it comes a time that we need to, okay, we said that we needed that in order to calculate, let's say, proper inertia for this. And to do that, let me bring this part still a little bit down because we're going to need it as a reference. This one here. Let me try to grab it all. Yeah, maybe here. Yeah. So let's see. Let's start calculating the inertia for all these processes. So I'm going also to divide the inertia into inertia 1 and inertia 2. Inertia 1, inertia is equals to inertia kind of, no, it's not equal, kind of. Actually, we start defining inertia in X and inertia in Y, with respect to Y. Great. Let's start with this one. So the moment of inertia of this combined section around this X-axis. So to do that, as I mentioned, we need to take care of the thing that the inertia as formula here is presented as with respect to the centroidal axis, which we have not, we have now kind of for each individuals, but the centroidal axis of these areas or sections is different from the centroidal axis of the whole combined section. So we need to do a manipulation to be able to find what's happening there. And that manipulation, or what we need to include in our calculation is, for example, that the inertia in the end of this one, of any part or any kind of with respect to any axis for this example, is going to be the inertia I know with respect to the centroidal axis, which happens to be this one here, plus something that is going to take into account not being that the centroidal axis of the sections itself are not coincident with the centroidal axis of the combined section. And that is called kind of using the parallel axis theorem. And that's kind of means is that you have to multiply the area of the section times the distance from the of the centroidal axis of that section to the centroidal axis of the combined area section. And this is let me mark it here. This is basically parallel axis theorem. Yeah. So let's do it by piece by piece. So I know that the x direction is going to be formed by the moment of inertia of the first area of the first section there and the moment of inertia of the second one. So let's just put it down there. I believe it's going to fit here. Yeah. Let's see. Then the moment of inertia of the first part is going to be what? It's going to be this one here, and that's going to be added to the difference of position. So I'm going to have, for example, for area 1, I'm going to have that is base height to the cube divided by 12. So I'm going to have the base is 150 millimeters times the height, which is 20 millimeters, and that's going to be to the power of 3. Yeah, and this is going to be divided by 12 plus the complement here, which is going to be the area of that section, and the area of that section is going to be 3,000 millimeters square, times the distance from, let's put it in the way, from this point here, use another color, from this point here to the x-axis. This distance is going to be what? It's going to be 34, which is the distance from the top to the x-axis, minus kind of half of the height of this, let's say, first section. So that's going to be 34 millimeters minus 10 millimeters, and this is square, and this is millimeter square. So this is going to be 24 millimeters. Yeah. Plus the moment of inertia of the second part of the T section, and that's going to be, let me open up a bracket here, the moment of inertia with respect to its centroidal axis, which is going to be the base, 20 millimeters, times the height, which is 100 millimeters, the cube, that's going to be divided by 12, plus kind of to take into account the difference of position on the centroidal axis, and that's going to be the area of this second section, which is going to be 2,000 square millimeters, times the position or the distance from this center here, which other color I could use, this center here, to the centroidal axis. Yeah. And that's going to be, to know that, I need to know, for example, what's the complementary distance from here up to here. It would be easier to know it that way. This is then, is it kind of, this is 100, 120 minus 34, that's going to give me 86 millimeters. Then this means that the distance from this point to this point is going to be, how much is going to be? If I kind of subtract 86 minus 50, which is this distance, is going to give me that number I want. So it's going to be 86 minus 50 millimeters square, square, and then that's going to make the cut here. Great. Now let's calculate that. Let's make the calculation of that. Let me clean up this. Then I'm going to have, put it a bit larger here. The first part is going to be 150 times 20 to the power of 3. That's going to be divided by 12 plus 3,000 times the difference of 34 minus 10. And that's going to be, no, 3,000 times 34 minus 10 square. Yeah, looks right. Plus, then, so the big one, oh no, let's just call it like that. And then the other one is going to be 20 times 100 to the power of 3 divided by 12 plus 2,000 times 86 minus 50 square. Yeah, and then I can do A plus B, and that's going to be, here it's a big number, yeah. So this is going to be equal to, let me put it in this way here. That's going to be 6. Again, I need to, yeah. Going to just kind of put it in scientific notation here. It's going to be 6 point, yeah, 0.087 times 10 to the power of 6, and the units is going to be in millimeter to the power of 4. So we have found our first moment of inertia. Questions so far? Let's find the second one, the moment of inertia with respect to the y-axis. And if I look back here, it is important to notice that for the y-axis, there is no need to use the parallel axis theorem because the centroidal y-axis of the combined section is coincident with the individual y-axis of these two sections. So I just need to use this simple formula here, and that's going to do the whole work that I need to do right now. That's going to be then for, let me write it here. The moment of inertia with respect to the y-axis is going to be equal to, the first one, the upper one is the base. Well, now it's different because now the base is going to be looked from this side here. And that's going to make it that, is the base times the height. And the height is 150 millimeter, and that's going to be the power of 3. This is going to be divided by 12 plus the base of the second section, which is going to be 100 millimeters times the height to the power of 3 divided by 12. Great. Let's calculate that. I'm going to put an equal sign here. I'm going to have then 20 times 150 power 3 divided by 12 plus 100 times 20 to the power 3 divided by 12. And that's going to give me that also big number, and I can round it up to 5.0, it was 692 times 10 power of 6 millimeter to the power of 4. All of this has been done to select the moment of inertia I would need to use in my problem, because let's remember the buckling happens to the side of the weakest moment of inertia. By comparing these two moments of inertia, kind of the one in y and the one in x, I can kind of already say that the moment of inertia with respect to the y-axis is smaller than the moment of inertia with respect to the x-axis, meaning that this is the moment of inertia I need to use in my calculations. Great. Now that I have calculated and selected that moment of inertia for my formulas, the purpose of that was to include it here so I can calculate the radius of gyration, which is one fundamental component of Rankine's critical load. Let's do so. So now I can calculate that radius of gyration because I know what's happening there or what should be used. Sorry, what should be used. So radius gyration is going to be K equals to the square root of the inertia, which is 0.9, 9.692 power of 10, sorry, 10 times 10 to the power of 6 millimeter to the power of 4, and that's going to be divided by the area of the combined section according to the formula here, and that area is going to be 5,000 square millimeters, and 5,000 square millimeters. If I make that calculation now, I'm going to have square of 6.45.692 to the power times 10 to the power of 6, yeah, divided by 5,000. Yeah, 33.74. So this is going to be 33.74 millimeters. Because square, this cancels with this one, kind of stays millimeter square. Square root then results in just millimeters. Perfect. I think I have now all the components needed to use Rankine's critical load formula. And just to validate something, I'm going to write that L is going to be equal to L in this case, and it's going to be 4,000 millimeters. Kind of the effective length is going to be coincident with the physical length of the column because of the type of connection it has. Then, I know it already. So let's then apply this formula here, Rankine's critical load. Yeah, right. Great. So we're going to have that P equals to, we have on the upper part sigma C times the area of the section, and that's going to be divided by 1 plus Rankine's constant times the relation of the length of the column and the radius of gyration, and that's going to be squared. Then it's going to give me 320. We said that we were going to use newtons divided by square millimeters times the area, which is going to be 5,000 square millimeters, and that's going to be divided by 1 times the Rankine's constant, and we said here that's going to be 1 over 7,500, and then let me write it here, 1 over 7,500 times the length, effective length of the column, that is 4,000 millimeters, divided by the radius of gyration, and that's 33.74 millimeters. And this is going to be squared. How much is this? Let's calculate it. Let me clean up this. So on the top we have 320 times 5,000, and on the bottom we have 1 plus 1 divided by 7,500 times 4,000 divided by 33.74, and this is going to be square. Yeah. So 556,000 something. So then the critical load according to Rankine is going to be P equal to 556,760 newtons. This is the critical load. And then the safe load, we said that was going to be the critical load divided by the safety factor. In our case, is 3, and that's going to be safe load equals to, let's divide that by 3. Let me do it straight away without A divided by 3. Is it 3? Yeah. Is, yeah. 185,560 72. Yeah, 0.1, why not? And there you have the solution to this problem. Questions so far? So let's recap this example. So we have a T-shaped section, which is, let's put it this way, not conventional. And we are assuming that because of the values they are giving us, and there is no any reference to any commercial section or something like that. And they're asking us to use Rankine formulas to calculate the buckling load, or critical load, when this is used as a column. We know that both ends are hinged, and that's going to give us the conditions to calculate the effective length to be used in the formulas, as Rankine uses the crushing load as a combination with the buckling load to determine this critical load. We have to have the crushing, let's say, strength of this beam. And as we're using megapascals, we are just kind of saying, okay, let's keep working everything in millimeters and in newtons because it's a straight translation from megapascals. Then they have to give us the Rankine's constant, and we know that because, or if we didn't know that, then we need to know what type of material is being used, and then based on that, we can use some tabled Rankine's constants, depending on the material we have here. And then in the end, we're asked to calculate the safe load this column can resist if we used a safety factor of 3. When then I postulate the Rankine's critical load formula, I know that there are several components of the formula which are known, like the crushing strength, the constant Rankine's constant, the length is known because knowing the type of ending, I know what's the effective length, but I don't know right away the area of the section or the radius of gyration of that section. To calculate that area, I just take advantage that these are two well-known areas, two rectangles, and then I can say that the total area of that combined section is the area of the upper rectangle plus the area of the vertical rectangle. Let's call it in that way, and that's going to give me this result that the combined area is 5,000 square millimeters. Now this is tackled, but if I want to know what's the radius of gyration, I need to know what's the moment of inertia. And as the section is non-symmetrical, then I need to calculate two moments of inertia around two axes that I chose to use the centroidal axis to the combined section to do that. And then I stepped into the problem that the moments of inertia for these well-known areas is very clear. They are tabulated. You can find it elsewhere, but those moments of inertia are defined according with respect to certain axes. And one of the axes is, for example, the on centroidal axis of the section, or one kind of, let's say, end, or kind of, yeah, one end of the section. But now the centroidal axis of the combined section are situated differently from the centroidal axis of the individual sections, and I need to use then the parallel axis theorem to find what is kind of the proper moment of inertia I should be using there. And as I have two sections, for example, when I want to calculate this moment of inertia about the x-axis, I kind of also take advantage that they are two well-known sections, rectangles, and then kind of, well, the moment of inertia around the x-axis is going to be moment of inertia of the first axis plus the moment of inertia of the second axis. But now to use the parallel axis theorem, I need to know what's the location of the centroidal x-axis. And to do that, I use the equation for centroidal axis, which takes into account the contribution of each one of these areas to the position of the centroidal axis, and which is presented right here. I go ahead and find out what are the moments of inertia around the x-axis, found what is the moment of inertia about the y-axis. Now the moment of inertia about the y-axis is simpler than the one on the x-axis because the centroidal axis of the combined section coincides with the centroidal axis of both individual sections. Then I don't have to apply the parallel axis theorem in the y-axis because of that. Then when I found the two values of those moments of inertia, I compare them and I get to see that the moment of inertia in the around the y-axis is smaller than the one on the x-axis, meaning that this is the one I need to use for my calculations. And the reason for that is that the column most probably buckle kind of towards this or around this axis. And that's kind of the situation I need to consider. And now I can calculate the radius of gyration here with the known quantities, which give me this value. I validate that the effective length of the column equals to the physical length of the column because of the ending condition, which are hinged and hinged. And then I can proceed and calculate the Rankine's critical load, which is giving me this value. And finally, I can calculate the safe load by dividing the Rankine's critical load by the safety factor, and I get this result.